The physical world around us is becoming more and more connected. Pretty much every major engineering application sustaining today's modern life, social networks, electric power systems, and transportation systems are manifestations of complex, large-dimensional processes that function through interconnected networks. The amount of information transmitted across these networks can grow at dizzying rates. Their size can easily go up to several hundreds of thousands of states distributed over hundreds of miles. The conventional mindset of designing a single, dedicated control box in feedback to an open-loop plant is no longer effective. Instead, what one needs to design is a system-wide controller. For example, the 1996 power grid blackout in the US West Coast was caused by a minor disturbance. What would have saved it from the catastrophe was the use of wide area control, where different parts of the network would have been permitted to exchange state information and take coordinated control actions. The lack of global control caused these generators to oscillate as 5 separate groups and finally disintegrated the entire Western interconnection into 5 separate islands. You may ask then, does today's technology allow us to control an entire network? The answer is yes, but the challenge is to design a controller for a huge network with so many components. The first challenge is computation. Computation cost of optimal controllers is proportional to the cube of the system dimension and can become intractable when the network size is huge. The second challenge is communication. Conventional control designs usually produce a dense feedback topology, which means that every node in the network must communicate with every other node in real time. This can lead to data flooding. How can we overcome these challenges to control a large network? The answer comes from the observation that most engineering networks, no matter how complex they may look from the outside, deep down often exhibit some kind of clustering or grouping structure within them. For example, in the 1996 blackout, generators that were geographically close to each other reacted similarly towards the disturbance and thereby formed 5 major clusters. The definition of a cluster, however, is not limited to geographical closeness. It can be any structural and behavioral similarity shared by the network nodes. For example, solar panels, wind farms, and batteries can each be considered as individual clusters in a smart grid given their similarities in power generation and consumption. We introduce a method called control inversion that exploits this clustering property of large networks to develop tractable controllers for them. The first step is to project the network model into a lower dimensional space using the idea of structured projection, which basically amounts to aggregation of the dynamics of these nodes inside of the cluster. Clusters in the original network thus become supernodes in the reduced order network. The second step is to design a controller for these supernodes. Since this system has a much lower dimension than the original, the control design becomes numerically cheap and easy to track. Finally, this lower dimensional controller is projected back to the original system for implementation through an inversion projection operator. This inversion can be done using a simple 2-layered hierarchical architecture and therefore is also numerically cheap. Here's how the overall implementation works. Nodes inside of each cluster send their measurements to a designated cluster coordinator. The coordinators perform an averaging operation on these local measurements and exchange the average measurements among themselves. Notice that in this process, data privacy is maintained between clusters since no coordinator can access the exact measurements of any node from any other cluster. Each coordinator computes a distinct control signal based on the averaged measurements only and broadcasts this signal to every node inside his cluster. The architecture requires significantly fewer communication links than a conventional controller. Our proposed idea of control inversion is a promising tool for controlling any cyber-physical system that suffers from the curse of dimensionality. While, of course, the applicability of this approach demands that the original network exhibits sufficiently good clustering, but such properties are common in most physical networks around us. This idea can also be extended to big data applications in signal processing and machine learning, such as compressed sensing, rank reduction, and data compression. We hope that this video has motivated some thoughts along these topics as well.